Hey there, Math Club. This is Noah. In our last episode, Linear Thinking, Pete and I talked about using a linear system of equations to solve a puzzle. Near the end of the episode, Pete mentioned that one practical application for this kind of math is helpful in urban planning, specifically in the area of traffic flow analysis. We thought it would be easier to understand this part of the conversation if we included visuals, so we put together this video bonus. I'd love to hear how these systems of linear equations can help with urban planning and traffic flow.
Yeah, let's see if we can cut everybody's commute time down. Okay, so the situation that you want to imagine is a complex network of streets. So streets running into one another at various types of intersections. Imagine the nearest downtown city you know about with its grid of streets. Some of them may be one way, many of them will be two way, but there is a way for us to build a linear system out of a network of streets like that.
Well, can you help us understand how to get started on that? Like maybe with a very simple case?
Yes. Let's put ourselves in the mindset that we are in a math club station wagon driving down some one-way highway. So I'm going to simplify by making things one way. We're driving on some one-way highway and we come up into a T intersection. The street that we're on cuts perpendicularly into a cross street. Now this cross street, I'm also going to simplify, and here's how. From our starting point, we can either turn left, at which point the traffic will only flow off to the left. It becomes one way in that direction. Or we could turn to the right and flow in a one-directional flow off to the right. So we have a T-shaped intersection and everything involved is going to be one way only. Can you picture that?
Got it.
Okay, just perfect. Now, let's say we've got a camera set up measuring traffic flow on the street that we started at, and that's highway, and we know that there are 50 cars an hour that come past this camera, which means 50 cars are going to come into this intersection. And we want to know what is going to happen numerically with the cars when they enter that intersection. How can we model that?
Well, we could count the number of cars that go to the right and then set that as a variable, I guess R, and say R equals however many cars went to the right.
And we could do the same for the number of cars that go to the left, right? Let's use the variable L. So 50 cars come in, some quantity goes off to the right. We're tracking that with the variable R. Some quantity goes to the left. We're tracking that with the variable L. And what can we do with these variables and this number 50?
Well, we can definitely say that whatever R is, L is 50 minus R, and vice versa. Whatever L is, R is 50 minus L.
That's right, because the same number of cars that come into the intersection have to leave the intersection. So the number that come in is 50. The number that go out is L plus R. So this gives us an equation. 50 equals L plus R. Hey, that's a linear equation, just like the soccer ball problem.
Okay, then what do we do next?
Well, that very simple model can be extended by adding additional intersections. Now, we're not going to go into the model itself, but I want you to picture some fairly busy and intricate downtown network of streets. So let's say you've got dozens of intersections, and at each intersection, this same rule applies. The number of cars that enter the intersection is equal to the number of cars that exit the intersection. And because traffic that enters one intersection will leave it and flow into some other intersection, that's how different variables algebraically are linked together. So each intersection represents a single equation. How many unknowns do you have? Well, it depends on the characteristics of those intersections. But you could imagine in a city like, let's say, Houston or San Francisco or Chicago or Seattle, we would have many, many equations with many unknowns. And then linear algebra and techniques for solving linear systems could be utilized.
Okay, I hear that. But right now, I'm just seeing a bunch of little cars driving around and being counted. How could we turn this data into a linear system of equations?
Right. Good question. So let's first fast forward to a point in the simulation where lots of cars have driven through the grid. Can we do that?
Sure. How about 50 again?
Perfect.
Okay, there we go.
And now let's just focus in on two adjacent intersections and think about what equations we could use to link them together.
Okay.
Let's look at the first intersection where the cars enter the grid, and let's take it as given that there are 50 cars that come into that intersection. Now, because there are three directions that cars can take exiting the intersection, we will need three variables, one for each of those directions.
All right, so let's call that intersection 1. And then we can use R1 for the cars heading out to the right, L1 for the cars heading out to the left, and U1 for the cars continuing to head straight up the screen.
Good. And if we put it all together, we get an equation. L1 plus R1 plus U1 equals 50. And we can see from the numbers in the video that that equation is actually true.
Right, because 18 plus 13 plus 19 equals 50.
Now take a look at the intersection directly above the first one, and let's call it intersection 2. In this case, we have one incoming direction and two outgoing directions. So we'll need a total of three variables to model this intersection.
Well, we already have a name for one of them. The number of incoming cars was U1. Or do we want to give that a new name because this is a new intersection?
We don't. We definitely want to use the same variable, namely U1, because that's how the algebra indicates that these intersections are related to one another. We do, however, need two new variables, one for each of the outgoing directions.
So to be consistent, those should be L2 and R2, right?
Right, that's great. And so intersection 2 can be modeled with the equation L2 plus R2 equals U1. And now our linear system has two equations. L1 plus R1 plus U1 equals 50. And this new equation, L2 plus R2 equals U1.
And since both of those equations share the variable U1, can we do some substitution to see how they relate to each other?
We could do that, but we probably wouldn't. And there are two reasons why. One, we have several more intersections to model, so we'll want to gather all of the equations together before performing any operations on them. And two, the size of this system is large enough that we'll want to use a more systematic approach, something called row reduction, which achieves the same goal as substitution, but is more effective when working with complex linear systems.
Oh, okay, gotcha. There are 7 intersections here, so we'd end up with a system of 7 equations and a whole ton of variables.
Right. Now, we haven't named all of those variables yet, but that's the general idea of what city planners would do when working with a system like this.